rough idea of grading. I will try to put up some ciphertexts and let you guys test on them, but I'm nervous about that because I can't even guarantee that my ciphertext will be, the best one. I'll try to come up with a few for you guys, okay? Any other questions about the assignment? Yeah.
So for part 3, you want us to print out the key or the key?
Because it's equivalent, right? If you give me the key, then I can just run your decryption out. Yeah.
So then do you want just the best key or a list of clauses?
Good question. I will be comfortable with any of them, but if you put out a list, we will accept that as an output. So that's fine. A ranked, preferably, list, not like if you give me 10,000 keys and one of them is right, that's not quite the same. So I will let the TAs know that you might output a list separated by new lines up to some reasonable number of keys. Okay, but if you put out zillions of keys, it's not going to look so great. Okay. Any other questions? I hope at least the grading side of this is pretty easy. The doing, maybe not, but the grading side should be pretty easy. Okay. Yes?
So we talked about the answer to question 4 in class last time?
A little bit. Inadvertently, maybe.
Okay.
Yes, possibly. Question 4 should be relatively easy, I hope, for you guys. Okay, good. So the assignments due this Wednesday night. See the Piazza for any other questions. I think a few other questions I might not have addressed are there. Long ciphertext and so on. Okay, TA office hours. Alicia is the head TA. And we have 3 CAs now who have not quite gotten organized into actually, being CAs. We're trying to get them organized by Wednesday night so we can actually grade your stuff. But Alicia's office hours are tomorrow from 5 to 7. Normally, I think they're 5 to 6. He will post on Piazza, or maybe already has the exact room information. He's also going to give a weekly lab review session, which sadly this week comes a little after the assignments due, so I expect he'll have low turnout. But coming up, we're going to move right along and try to get out new assignments. Will be a lot more relevant, and you may want to come to those. They are in Bloomberg 178 on Thursday evenings. That's not 5/, that is 5 to 6 p.m. Okay, and that will include this Thursday. He'll post about that on Piazza. And we're going to try to get A2 out because if I looked at the syllabus that I have up, and it insists. It has a couple of dates that I fixed, but it insists that I get these things out quickly. I want to get them out quickly because I don't want to have lots and lots of time lag in between these assignments. And that one's going to deal with public key encryption. Okay, good. Anyone have any news or questions before we have news? Okay, I saw a hand go up, but maybe I was
News.
okay. Shoot with the news. Go.
The ciphertext they got deciphered last week or this weekend.
Okay, tell me about it.
The text that you described as indecipherable for 100 years.
Yes.
Turns out it's a middle-aged Hopkins.
Well, it wasn't. In fact, that was actually, they didn't do any homework at all. Everybody on the internet bashed it entirely, and they posted an article a couple days later saying that they weren't sorry, but that someone else was wrong. And proceeded to name bash him. But so basically someone who didn't have any cryptography experience started making assertions about the distribution of characters, saying that these characters, of which there are relatively few, were actually multiple syllables, but it was bad claim, sensationalized and not checked in on. There is some recent work on working on this encryption, but it has nothing at all to do with this guy.
Okay. Okay. So there is controversy. There may be a solution. There may not be a solution. It's not clear that this guy really solved it.
It's the normal state where somebody says they solved something, and then you got the academic world saying, no, you're wrong.
It's very possible. However, in fairness to the academic world, this guy has only solved 2 lines of the text. So I think once he proposes his key, and we can actually go through and we can look at every single page, I think maybe it'll be a little more believable. So we'll see. We'll see. It could actually be solved. In which case, it turns out to be a treatise on bathing from the 1600s or something. And these pages describe what plants and how you boil the things, and basically their recipes for concoctions. And who knows? Maybe it does have the secret to immortality in there, but it's going to involve boiling a lot of flowers, which is not very exciting. Okay, so yeah, this is interesting. But I mean, it's a live point that even classical, perhaps ciphertexts, years later can sometimes be very challenging to break. And it's possible that this isn't a ciphertext, it's still fake, but there's stuff in here that is very difficult for us to crack, and we are still arguing about it. Any other news?
The advertised data breach.
Oh yeah, tell me about that.
Yeah, so from what I read, I mean, it just seemed like the information they were giving at the time was that there was a web application vulnerability that they exposed. I didn't get to see like which one that was or anything like that. But 143 million people were compromised with sensitive data like credit card numbers and social security numbers, and their stock crash and a lot of that.
Good, okay, yeah. You want to add to that, or?
Adding to that.
Yes.
Another thing is that they provided a tool where you could check whether you were one of the people who installed.
How does that tool work?
Also, they, in order to check that, they also made you like sign it, like you basically had to agree to like not suing them or like not taking any legal action.
Did their tool actually tell you anything useful about whether your data was breached? Did anyone try it?
It said your data may have been compromised.
Well, the other thing was they figured out that putting your stuff in there didn't mean that it was going to return a reliable result.
Right.
Yeah.
So, you put your stuff in there, you agree not to sue them, and they give you an answer that, who knows, could be true, could not be true.
So it seems like it's basically a random number generator. That
Exactly.
decides whether- Okay, yes.
That random generator seems to generally report a yes. But the other thing is they emitted PIN numbers, and people's PIN numbers are precisely the timestamp on the server at the time that they submit their
Oh, that's
request. Yeah, so even a lazy programmer would hash it, but these guys are just happy to use, they all start with 09 because it's September and so on. Also, all of the executives cashed out after the breach in July, and then in addition to that, they lobbied against the CFPB, which is coming up to the Supreme Court pretty soon.
great. Okay, so your data is poorly secure. What do you think could have stopped this attack? Anyone? Well, hang on, someone else picks it up. What could have stopped this attack? What would you have done? You have been hired by Equifax to be the sacrificial lamb for the next breach. What are you going to do to try to save your career? In all seriousness, what are you going to do?
Massive code reviews.
Massive, okay, that's not the craziest idea I ever heard. It's a really good idea. Get some good security people in. Stop using like broken web frameworks. Yes, well,
Yeah, well, I was gonna say something similar, like, you get a consulting company, people who actually know what they're doing, then rather than relying maybe like now you have people doing it, you don't know what they're doing, I don't know.
yeah. Does anyone know their VP in charge of security and compliance was a very skilled lawyer, but apparently had no technical expertise. So there seems to be a lack of technical expertise that would have actually protected this stuff. What else would you do? Yes.
Like bounty?
A bug bounty, that would have been good, although 143 million records is like the best bug bounty, right? I'm sure that's worth a lot of money. So, yeah, no, I mean, that's true. I don't think they have anything else. What else would you do?
Well, I'm not sure if they were storing these records in plain text. That would be a big no-no, I guess, in the database.
Okay, so let me ask a question. So, yes, this is probably the first thing a lot of people say is, why wasn't the data encrypted? But there's some answers to that. Why would it be hard to encrypt the Equifax data? What would make this a challenging thing?
Because it's being used.
Right, it's a hot database, which means that people are constantly, or systems really, are constantly making queries on this data. And so at least some of the data has to be available to those systems, which unfortunately means that if somebody hacks into one of those web applications, they too can make queries. So is there anything you can do about that? Yeah. Well, I don't know if you can answer
I
that.
was thinking just let Amazon host it and not have to worry about hosting that database yourself.
Well, it's not,
That way much more secure.
it's possible though. I mean, remember, when you host a database, you have a whole chain of things that can go wrong, right? Somebody can get into the database, but they can also get into your web apps and the servers that are accessing the database, and they can use those to query the database. So there's an entire series of different places, and we today do not know what happened. We don't know if they got into the database server and just dumped all of the files. We don't know if they accessed an app, but it sounds like maybe they got into a web app and then queried. So, here's the question. So what do you do about that? Well, how do you deal with that very hard problem of trying to keep a hot database, but making sure that if someone, maybe even a malicious insider, starts accessing 143 million records, you can detect that something weird is going on? What would you do?
Rate limit, figure out what the normal is, and if somebody starts select all,
Good.
select star from database, don't let that go through.
Good. So it seems like that's kind of the strategy, right? So try to encrypt at a low level, block off all the different ways, encrypt as much data as you can, up until you get to an application, that really has to know the keys so it can access that stuff, or maybe it's a shim in between an application. And then here, the only way you're going to be able to make this work is putting some kind of access control logic that is able to do auditing, and you mentioned maybe rate limiting, and maybe other kinds of intrusion detection that look for that select star and say, hey, I don't think that, my legit users are supposed to be doing select star. So it's hard. It's a really hard problem, but this is sort of the solution. I can't even read what I just wrote there. This is the solution to actually making this stuff secure. It's a really hard thing, but companies are starting to do it. Encryption is really a part of it. It's just a low-level part. It's not the only part. Good. Any other news? Slides, Equifax? Yeah.
There was something like 500,000 pacemakers were called at the FDA because they had security.
Really? I like pacemakers. What was the problem with these?
There was just a giant list of problems. It was almost like they were designed without security in mind at all.
Go ahead and add on to that.
The end result was effectively that if you could kill someone at range who had a pacemaker inside them.
Good. Okay, that sounds kind of bad, right? Like actually killing people with crypto. It sounds like a real problem that you want to stop. Okay, I actually was I was involved in this somewhat. I was hired as an independent expert to come down and look at these the results of the company that found these problems. And what we discovered, or what they had discovered, and they showed us, was that these pacemakers were using 3-byte RSA, 24-bit RSA, to do the authentication between the device that's supposed to send shocks to human beings and the actual implantable device in their body. And so not only are they using 24-bit RSA, which, as we will learn shortly, is not very secure, but they were also using a 24-bit hard-coded override password that allowed you to, even if you didn't solve the RSA stuff, just use that as a password, a master password, to send commands over a radio to these devices. And these devices can actually send a shock that will put your heart into, atrial fibrillation, where they no longer pump blood properly and you do die. So there's a lot of really scary stuff in there. 500,000 old people mostly are going to have to go into their doctors and get a firmware update into these devices. So like how long that's going to take, I have no idea. It's a really, really interesting situation. Yeah.
There's another situation where this is interventions in response to people literally being killed. So there's a reporter in Syria in 2012 or 2013 who was killed by a government attack because her location was identified by radio frequencies being emitted by her phone, even though it was in airplane mode. And so Edwin Snowden and an engineer from MIT have put together some hardware for externally putting it on the phone, which assumes that the operating system will be compromised, and then
So you're actually going to measure from the outside of the phone.
right.
That's really interesting. Yeah, no, I've seen that. Bunny Wang is a smart guy who does this. Yep. Yes, last one.
There was another leak in which ultrasonic sound can actually enable Siri or Alexa from ultrasonic transmitter.
Yeah.
So that endangered a lot of smart cars and like all the smart devices.
Good. Okay. Yeah. So people make assumptions about what input's going to look like, and smart people figure out ways to get around those. So that's kind of the story. Okay. We'll stop. Otherwise, we're going to have no time for actual class today. So if you have other news that's interesting we haven't covered today, hold it until next time. One thing I want to do. Sadly, this board won't remain uncleared, but I want to add this number. And I'm going to keep this in some other location. This brings us to the number of records breached. It is September 11th. We are at 143 million. Do you think we will get over 1 billion by the end of this class? Raise your hand.
Yes.
Okay. That's a small number of people. Well, we will see. How many people think over 500 million by the end of this class? Okay, good. So we'll just keep that in mind as we go and we'll try to follow this guy. I have no idea. I'm not gonna take a horse.
Are we up to like 144 with the pacemakers, or?
Well, that was a little before. Let's start with the 143 as a base. Ooh, what?
There's 300 some million heritage.
Oh, yeah, no, but that's also including kids who hopefully are not in Equifax's databases. Okay, so I want to go back and I want to pick up where we left off quickly. Okay, so we really breezed through classical crypto, and there was a reason for that, which is that you guys were being forced to jump into the deep end and kind of self-educate on at least one very important piece of classical crypto, which is the Vigenère cipher. Now, quickly, can somebody tell me why is the, okay, let's go back to basic cases. Somebody tell me, what is the shift cipher? You probably have encountered this in the course of learning about Vigenère, so somebody quickly tell me what the shift cipher is.
It started as the Caesar cipher, and you take a set offset, and for each character you advance it by that number of offsets. So, A plus 3 might equal D, B plus 3 might equal E,
Good.
and then it rotates at Z.
Very good. Okay, so the shift cipher is an ingredient of the Vigenère cipher. You guys know basically what it does is you pick an offset which can be anywhere from 0 to 25. and you add to each letter in the plain text a certain number of positions. You move it a certain number of positions around the alphabet wheel, and the alphabet wheel is something that's kind of, people actually used to build wheels and boxes to sort of show this. The key being that if your shift is 1, A becomes B, B becomes C, and of course when you hit Z, Z becomes A. So this is basically what Visionaire is doing. What is quickly, very quickly, what is the weakness of the shift cipher? Yes?
Letter frequencies?
Okay, before we get to, don't dive directly into letter frequencies. What's even worse about it? Yes?
Can brute force it 26 times.
Good. Okay. The weakness, the super weakness, is that it has a very small key size, right? The key size is 26 possible shifts, of which one of them is the identity transformation, meaning it doesn't actually produce any like kind of scrambling at all. People like to talk about how Julius Caesar loved this cipher. I don't think he really thought it was a secure cipher. Even Julius Caesar probably knew. I think he just used it for like light obfuscation of messages passed around. It was not intended to be super strong. Okay, so what we have is an example of small key size. Now, we talked about the substitution cipher as being a potential solution to that. Substitution ciphers, like in this example, replace every letter of the alphabet with, for the simple case, an alphabetic substitution cipher, replace them with a different letter. So what does that do to key size? How big is the key size of an alphabetic, meaning, let's just say one alphabetic character replaces every plain text character? What is the key size of an alphabetic substitution cipher? Is it 26? Is it bigger? What is it? What's that? It's some power. Give me something more precise. Very good. So you start out, I want to pick a letter for A. I have the entire alphabet to choose from, so 26. Now I want to pick a letter for B. Well, I can't use the one I just picked for A, so it's time, so it's a factorial. But you're both basically correct. So we're talking about a vastly larger key size, an exponentially larger key size. So substitution ciphers seem like, just from a key size perspective, they should be very strong. But as you guys were saying, and of course you figured out by now, substitution ciphers are not terribly strong because what? What leaks? Frequency. And if you want to put this more generally, why? Why does letter frequency leak? What is it about them that causes this leakage? Okay, the plain text is English, but what is it about the cipher that makes it so particularly insecure for that kind of thing? Yes.
If you figure out one letter, you have every other letter of
Okay,
that
good.
type.
So the key, the bits of the key, if you were to put it this way, are not tightly intertwined. There is an attack that allows you to kind of figure out part of the key at a time. That's true, so that means you don't have to do full brute force. You can do brute force on small sections of the key, and it's actually useful. Very good. What else? What else? Talking about this letter frequency thing, yes.
So even more than letter frequency, there's structure within the text, meaning that letters co-occur together in patterns because language has regular patterns.
Okay, but if we had a really good encryption scheme, hopefully we should be able to hide that. What is it about the substitution cipher that doesn't? Yes.
There's like a one-to-one relationship between the text characters and the subtext characters.
Good, and that causes patterns of the plain text to leak out. So if T appears twice, T will appear, whatever substitution character for T will appear twice. So that covers what you just said, and it also covers letter frequencies. It explains what's going on. We have a large key size, but key size is not everything. It's also other aspects of the cipher that can make a big difference. Now, I pointed out this is, guys remember what this one is?
Zodiac.
Yeah, one of the Zodiac ciphertexts. Now, there are a lot of ways historically that people tried to fix these problems. Not the key size problem, because actually substitution ciphers have big key sizes, but this kind of leakage problem, and they're all hacks when you get down to them. So this is not a classical, it's not really from classical times, but it's a good illustration. The Zodiac cipher actually has many different characters besides letters, and so instead of a simple table with a one-to-one correspondence, there are multiple ciphertext characters for each plain text in the Zodiac, allegedly, we think. Some of them have been broken, and others haven't. Well, that helps. It helps because now many of those patterns are obscured, because instead of having T always encrypt to the same letter, it could encrypt to multiple symbols. But all it is a hack. If you get enough plain text, even this hack is going to break, and sooner or later, you can pretty much see how to attack this. Okay. Yes?
Finnegan's Wake was actually pretty easy to crack.
Okay. I don't know what James Joyce's actual letter frequencies are. I will take a look later. Okay, good. So here we go. So this is kind of what the limitation of these simple substitution ciphers is. Now, when we start to get more complex into the Visionaire world, what are we doing that makes things more difficult? Vigenère is a very simple cipher. It's really just a shift cipher, but what about it makes it more complicated? First of all, let's look at the key size before we get into the patterns problem. What's the key size of a Vigenère cipher? Let's say we fix the key size to be 10. What is the key space of a Vigenère cipher? Yeah, so that's a big number. Alan Turing famously was able to do powers of 26 in his head. And he actually would go take trips to Washington, D.C. and be like, oh, there are 525 streets in this book, because he could just instantly do this, which was because he spent years cracking ciphers that were all alphabetic ciphers. I can't do that, but 26 to the 10 sounds like a very big number to me. So we know that there are large key spaces possible if you use good keys. If your key is kitty, it doesn't matter that you have a longish key, it's just going to be a bad choice. So if you leave aside the bad choices, seems like we're doing really well. But as you guys are learning, and I don't want to go into too many of the details, the appearance of a large key space does not mean a very strong cipher. But what you can see from Vigenère is that at least the complexity is going up, in the sense that we have a cryptanalytic effort that is going to be somewhat, some multiple of the amount of ciphertext is going to be needed, and a lot more work is going to need to happen. At the same time, you get a cipher that's very easy for a person to use. So it's a really good trade-off for longer keys of how you can get to more complexity. And the Playfair ciphers, again, even a little bit more complex, and so on. Skip past this. So what we talked about last time was one-time ciphers. And the interesting thing to me about one-time ciphers is that we're still really early in the development. We're using very simple tools, basically addition modulo 2. And we were able to take binary messages and turn them into perfectly unbreakable ciphertext. Now, somebody quickly, remembering that the way we did a standard one-time pad was to take a plaintext message and to XOR it with a key of equal length to get a ciphertext. What was the argument that you guys were using last time to convince me that this was unbreakable, assuming the key is as long as the message and assuming the key is perfectly random? Somebody tell me quickly. How do we get the claim of unbreakable security? Yeah.
For each plaintext, there's the same probability. For each key, there's the same probability of plaintext.
They're pretty much very close. Given a ciphertext, for every plaintext, there exists a key. And the probability of that key being the correct key, or if I do the same with plaintext, if you don't have any knowledge about which plaintext is more likely, the probability is equal, because remember, we chose these keys at random, and the choosing of keys at random gives every key equal probability. These are all assumptions. So you can actually do something very strong. Hold on. So you can actually build very, very strong encryption just based on those assumptions. It's really neat. And this argument, by the way, will come up over and over again as we get deeper into crypto, this kind of information theoretic argument that Claude Shannon proposed for why this is a secure encryption scheme. Okay, good. So this is how you build these things. Has anyone ever seen the actual one-time pad that spies use? They are a little different. One-time pads that spies use actually don't quite look like this. They are actually pads, and they have letters written all over them, things like this. And the letters may not even be uniformly distributed. There may be more E's and T's because those are more common. And so what happens when you want to send a message is you go through a one-time pad. I have a copy and you have a copy. And aside from these distributions of letters, they're randomly generated. And what I'll do is I'll say, I want to send you the message SOG, because I was about to say SOD. Let's say I want to say SOG. Well, I'll just pick off the position on the pad that these letters are at, and I'll send you that list of positions. Maybe it'll be an XY position. And if you make the assumption that these letters have been placed onto these pads at random, then there should be no leakage about what message you're sending. You can make the same argument that Shannon made for this kind of one-time pad. And so as long as you never use them twice, this is actually a secure encipherment system too. Okay, great. So one-time pads are very secure, but we don't use them. Why don't we use them? Remind me. Last bit of review. Shoot.
Because of the logistics of sharing the keys.
Good. It's a drag. We have to share keys. They have to be perfectly random, and they have to be as long as the message. And what terrible thing happens if we start to reuse them? We make a two-time pad. Okay, so I have encrypted plaintext 1 with K, and I've gotten ciphertext 1, and I'm going to encrypt plaintext 2 with the same key to get ciphertext 2. What bad thing could happen with the standard? Yes. Ah. Good. And what do you actually get when you write that out? What is? Let's just express this and we'll do the actual arithmetic. So you've got P1 XOR K, P2 XOR K, all right? And we're going to XOR these together. How does this, what do we get? What's the end result of this? Good. When you XOR these together, the K's actually cancel out, and you get P1 XOR P2. All right. Why is that a problem? Can you recover P1 or P2 from that mush?
Known plain text attack, it is one of the rules of hack. So if you had an encryptor which does this, and
Yep.
you encrypted your own ciphertext,
Okay.
you could just XOR the plain text.
So good. You're giving me an example. At heart, what you're saying is if I happen to know P1, because maybe I had some way of knowing that one of the messages, plain text, was whatever, now instantly I know P2 because I can just XOR and I can figure this out. Or if it happens to be that P1, I happen to know that it's like the null message, like a bunch of zeros, well, then a bunch of zeros XORed with any message is that message. Or if it's like, you know, maybe one of those messages, like if I have a Word file where there's a bunch of text, and then there's a bunch of null padding, which can actually happen in binary files, and then like some more stuff happens, and I happen to XOR this portion with a meaningful seconds plain text, well, this portion will pop through. So it turns out that this is actually a really big problem. In fact, there was a work out of some grad students here at Johns Hopkins and Jason Eisner, where they actually used NLP techniques to take two English texts that had been XORed together, and they found that very high probability, just given that XOR, they were able to extract both of the English texts using NLP models. And the reason is because there's tons and tons of redundancy in English text. So these things fail very hard when they're used twice. And there are lots and lots and lots of stories of them being used twice. And this will actually come up a lot, this idea of, oops, we accidentally XORed two messages with the same key. Turns out to be a big ongoing problem with real crypto systems that we use today. We'll get to that. Okay, good. So people had this problem throughout the classical era where they wanted to build things that were more complicated, but they kept running into the problem that human beings can't handle very much complexity. So they had this particular problem. If you remember our adversarial model, which I'll flip back to for just a second. If you remember our adversarial model, the idea of encryption is you want things to be very, very hard for this person in the middle to attack the crypto. But at the same time, you don't want things to be very, very hard for these two people who have the key. You want this to be very easy for them to exchange messages. So you want to build as much of an asymmetry between their computational effort as possible. It turns out that many of the techniques that human beings can actually implement themselves, not very easy to get a lot of asymmetry. Visionaire is kind of the limit of what human beings can actually do. So without hardware, human beings are limited. But once you start throwing hardware into the mix, you can add more complexity without making life too difficult for people. All right, so these two devices, anyone know what these, you know what this one is, don't have to tell me. What about the other one? What is that device? I don't know if you can see it very well from there. I don't know how to blow it up. It's a wheel, a bunch of wheels actually, with letters written on them. And they go onto a central spine. And the wheels can be removed and turned and kind of shuffled. Anyone know what this is? It's called a Jefferson wheel. Jefferson, because Thomas Jefferson allegedly invented it. Really all it is a bunch of substitution ciphers kind of organized in a way that makes it very fast and easy for somebody who knows the correct configuration to do something a lot like Visionaire. So it's really just a mechanical aid for traditional classical encipherment. It makes things faster. Ironically, this is not the actual Jefferson wheel that Thomas Jefferson used. This is a, I think it's an M102, it's an M94 device that was used in World War I. So we have Thomas Jefferson in World War I still using basically the same cipher technology. Not very impressive. In the 1940s, things get more interesting. Now, you guys know this is the Enigma machine. What did the Enigma machine do to make things more complicated? What was its innovation?
With every character, now I'm guessing at this, but with every character it reshifted the rotors.
Good. So traditional cipher machines have one substitution mapping. Traditional, meaning like things like this guy on the left. One substitution mapping which is always the same. So every character you go through, maybe you're using a different part of the key, but the key is the same. The idea that was really innovative with devices like Enigma is now that we had these wheels and these interlocking mechanisms, we could build a substitution cipher that actually changed with the state of the machine. Every time you pressed a letter, the underlying arrangement of the rotors changed. This is actually called a state cipher, meaning you specify the initial state, and then it basically permutes itself into different states over time. We're going to see a lot of examples of this when we get into stream ciphers. Okay, so these state ciphers are very powerful. They give you a lot more complexity. They're much, much harder to cryptanalyze because their complexity is there. A few more quick examples. I want to show you my favorite in just a second. That's a Japanese purple machine, very similar to the Enigma. This is actually reverse engineered purely from ciphertext, I believe. This is a Hagelin M209 cipher machine. This was one of the first crypto AG cipher machines. Let me show you my favorite, which is down here. This is a Russian Fialka machine. You look inside of it, it's got 10 rotors, but fundamentally the technology is not that different from the Enigma machine. What's scary, though, is this machine was used throughout the 1990s for nuclear command and control inside the USSR, or inside the Russian Federation, I guess, after that. It actually had a printer that could print and read punch cards, so it was actually that sophisticated, but still fundamentally the same tech. So this is kind of what was going on. All right. So the summary of even the classical era through the kind of mechanical era is that most of the crypto systems I've told you about here were ultimately broken. And what this means is that the sophistication of the attacker outpaced the sophistication of the crypto system itself. Many of these relied on secrecy of design, and when that secrecy was gone, the systems fell apart. If you recall, we had a principle, Kirchhoff's principle, that said not to do that. Even worse, these systems were often not evaluated for very specific kinds of attack, like chosen plaintext attacks, where I could get you to encrypt a message of my choice. Oftentimes, they seem very strong when all you had was ciphertext. But once you could leverage these more powerful attacks, they fell apart. There were very, very big weaknesses in the way that most key generation and distribution worked. And so basically, crypto for this period fell into an arms race between cryptanalysts and people who designed crypto systems, just constant improvement. Quick reminder, Kirchhoff's principle is that the enemy knows the system, or at least Claude Shannon's translation of it. In the 1970s, things got more interesting. They got more interesting because of these three groups of people. Can anyone name them? Which one? The third one. Okay, good, good, good. All right, so this is Shamir, Rivest, and Adam. Good, very good. These are the RSA inventors. Who else? What about the other two? Good. I put three guys in there just to throw you off, but yes. One of them, so Diffie and Hellman. This is Diffie, and I think this is Hellman, and that's Merkel, Ralph Merkel. I'm never quite sure which one's Merkel. So Merkel is a guy you may have heard of, or you will hear of later, one of their students. Okay, so that's Diffie and Hellman. They invented a key exchange protocol. So between these two, this was the invention of public key crypto. What about the guy on the left? Okay, if I give you his name, how many people will recognize it? His name is Horst Feistel. Okay, good. I have 3 hands, 4, 5, it's a few hands. Okay. Horst Feistel is the guy whose name, at least, is on something called the Feistel cipher, which we'll talk about in a second. This is a really big advance in symmetric crypto, which made a big difference. Many people actually say one of his students invented it, but whatever, he was an IBM. One thing you may notice is that I put a couple of different dates underneath the RSA invention, the Diffie-Hellman invention. That's because it turns out that public key crypto was not invented, at least we believe, by these folks. It was invented by some other folks who worked for the UK's GCHQ, which is their NSA, essentially. Cox and Ellis and another guy whose name I always forget actually claimed that they invented this a few years before, but they were not allowed to publish their inventions because of classification rules until the 90s. So that's a really sad story. But so for most purposes, we call these RSA and Diffie-Hellman. Okay, so what are the implications of what these people did? Well, the implications are that starting around the 1970s, there was this really exponential increase in the study and the usage of crypto. And the reason that happened is mostly because computers became ubiquitous. All of a sudden, with networks and computers, encrypting things was not just some military application, it was common. We all needed it. We started to see wide-scale deployment of cryptographic systems. And in the 80s, we saw the development of something really interesting, which was the notion of provable security. The idea that we could actually develop proofs, mathematical proofs, showing that certain cryptographic systems were secure under various mathematical assumptions, typically by reducing the security of the crypto system to some hard mathematical problem. Interestingly, this is not the first proof. I already showed you in outline the first proof of a crypto system, which is the proof that the one-time pad is actually a secure system. But that's a little different than the kind of systems that we use today, so we kind of separate those things. Okay, so the first thing I want to talk about in this kind of world of the 1970s, things that changed, is the invention of something in the 1970s called the data encryption standard. And the data encryption standard replaced really a lot of the garbage that came before it. And what the data encryption standard was, is it was something, where's my eraser? Something called a block cipher. Okay, a block cipher. Can somebody quickly tell me what a block cipher is? How many people know? I've heard this before. Yes.
I can't remember exactly what it was, but if I had the mark up.
It's okay.
Yeah, if somebody can remember it.
It's like a pseudo-random permutation.
Oh, wow, you're really diving into things. Okay, it is. It is indeed a pseudo-random permutation. Good. Could you give me a slightly less technical explanation? What does it do? Like, what is its profile? What do I do with the block cipher? You handed me a block cipher. What do I put into it?
If I have n inputs and I can output n outputs,
Okay.
and that's quite random, so you can see what the relationship between these two.
Very good. So when you say n inputs, really, just for clarity, you mean like an n-bit input and an n-bit output. Fantastic. So with all of these ciphers, one second, with all the ciphers we've been looking at, the classical ones like Vigenère and so on, we've been working first of all with these big 26-character alphabets because we're human beings. But now we want to deal with computers, so we're going to get back to binary. We did have binary with the 110 tag, but we're going to go to binary. Okay, great. So we're going to encrypt binary bits. Now, we're in these other ciphers like Vigenère, we were encrypting one symbol at a time, where the symbol was this 26-character alphabet. But now we're going to stop doing that, or we're going to do it at least in a slightly different way. The way a block cipher works is you have a pair of algorithms. Sorry about that. One of them is called the encipher algorithm, and it takes two inputs. Block cipher. The first input is a set of bits, or not a set, rather a string of bits, that we're going to say, it's a little L, is a string of L bits. We'll get back to what you choose for L. That could be anything. Okay? And the second thing, which we call the key, is another string of bits. And we're going to make that one, I'm trying to think of something, well, let's call it, I hate using symbols. Let's say it's lambda bits long. I'm sorry for using these weird characters here. Okay? So this is your key, and this is called your plain text. Okay. Now, what comes out of a block cipher? How long is the output? We put in L bits. How many bits are we going to get out? I hear people kind of muttering L. So let's go for it. Yes, the answer is L. If L is 64, like DES, that means we're going to put in 64 bits of data, consecutive bits of data. We're going to feed it into this block cipher, along with a key. We'll hold off how long the key is for the moment. And what comes out is also going to be, surprisingly, another L-bit output. Okay, so somebody mentioned the word permutation. Fantastic. What's a permutation? Someone give me a quick definition for permutation. Anyone? Come on, guys. Yes.
Like a different ordering of a certain symbol.
Good. Okay. Yeah. There's even the precise mathematical definition. Anyone want to try it? I'm looking for one-to-one and onto, right? So you guys basically a permutation. Yeah. Good. So here we go. So a permutation looks like this. Let's say we have the world's crappiest block cipher. Let's say it only takes in 3-bit inputs, so it only has possible integer representations of 0 through 7. Well, a permutation would basically have the structure that every possible plaintext input, once we set it up with a key, every possible plaintext would map to exactly one of the possible outputs, which is great, right? Why do we want it to be a permutation? Yeah.
Well, we want to have every input to have a corresponding output and vice versa.
Why?
Partially so we can decrypt it later.
Very good. So we want to be able to decrypt it. Two plaintexts map to the same ciphertext, and then I tell you I want to decrypt them. Well, you're not going to know how to go backwards from that because you've just collided and you don't know which of those two plaintexts to go back to. Fantastic. Which brings us to the fact that block ciphers have a second operation, and I'm going to draw this a little farther down because I don't want to crash into other things here. Okay, and can you guys guess what that is called?
Xbox.
Too specific. Decipher. Good. I was hoping somebody would say uncipher, which I would like. Decipher. Good. Decipher. Once again, it takes a key, and we will assume, I'm not going to, the same length, whatever, and it takes in the ciphertext, which is, again, an L-bit string, okay? And it spits out another L-bit decipherment, which hopefully, if everything has gone well, is the plain text. Okay, so the theory of a block cipher is once I set a key on both sides of this algorithm, I can put any message into this top part. I will get out another string that hopefully looks very different, has been ciphered, is scrambled. And then when I want to decrypt that string, I put the same key into the decipherment operation, feed that ciphertext into the top of the decipher algorithm, and wham, if everything went well and the cipher is not broken, then I get out the original plain text. So that's the definition of correctness for a block cipher. Fantastic. Okay. And we further made the requirement that this be a permutation, which is how we're allowed to know that we will, for a given key, always have a unique decipherment. So this should be pretty straightforward. Okay, great. DES happens to be one instantiation, one algorithm for performing this block cipher operation. It has a 56-bit key, so I'm just going to erase that. And I said before it has a 64-bit block. All right. How do we feel about 56-bit keys? Remember, earlier today we said that a size 26 key space was not enough. And then we jumped to a Visionaire which had 10 or 26 to the 10 or something. So now we know how many possible keys are there. Well, there are 2 to the 56 keys. All right, so if I give you a bunch of data that's enciphered with this DES thing, and I tell you it has a 56-bit key, which it does because it's standard, what is your first thought for an attack going to be? Yes?
Brute force it.
Brute force. Try every single possible one of those 2 to the 56 keys. And then, try it on the ciphertext, decrypt or decipher, and see if you get a recognizable plain text, which helps if it's actually recognizable. Great. Can you do that efficiently? I'm getting one person nodding and shaking their head. I'm getting one person nodding. I think this really depends on the word efficient. What does that mean to you?
Doable for a person and not an organization.
Doable for a person. How long does it take me? If I wanted to right now, let's say I have $100 in my wallet. I shouldn't have told you that. So let's say I have $100 in my wallet. How long will it take me using my $100 to get somebody to decipher brute force 2 to the 56 with that money?
So when this was first developed, the computing power was not as advanced as it is now. So at that point, it was measured in years or tens of years. I think it was in the early 90s they actually started building custom hardware that could work with that size key size, and got it down to about 10 hours. And I think they've done a whole lot better since.
So nowadays, there at least very recently was a service you could go to online. You could pay them $70, and they would crack the DES key for you. And I think their time was actually an hour, but I think they promised you a day. So we're down using what technology, by the way? Anyone know what you use to really crack things fast like this? GPU? What's that? Not GPUs are fast, but not even as fast. What would you do if you really wanted to do this?
ASICs.
Good. Okay, so ASICs, which are application-specific integrated circuits, you can build a bunch of these custom chips that implement the DES decipher function and actually just go through lots of keys. You can parallelize it a lot, try different parts of the key space and different parts of the chips. And somebody else, but if you don't want to build an ASIC, what's the next best technology?
FPGA.
Yes, and what's that?
Field programmable. It's an array of a ton of gates,
Good.
and you can configure them
Good.
to do whatever you want.
So back when DES was invented, the NSA actually looked at this and said, we're going to build a block cipher. We're going to limit the key size to be high enough that attackers can't break it, but that maybe we, with all our supercomputers, can. But now, about 40 years on, it turns out that 2 to the 56 is just not very strong, and you can buy hardware that can actually brute force your way through 2 to the 56 possible keys. So we do not use DES anymore, but it's an interesting case study because we can use it in other ways, and also because, because there are lots of things to do. So by the way, one thing I want to illustrate is, although I showed you that example with a 3-bit ciphertext input, it can be up to, in the case of DES, it's 64. It's still a permutation in the sense that all these different inputs go into different, have a one-to-one mapping. Sorry, stupid animation with that. Okay. going back, before we get to the specifics of DES keys and so on, when we talk about DES, we're not actually talking about a single permutation. Remember I mentioned that before you talk about this permutation, you have to set a key. DES and block ciphers in general are actually what we call PRP families, or permutation families. So every single key basically programs the cipher to pick a different permutation. And the idea should be that if I pick a key at random, you should not be able to guess what that permutation is very easily, at least. Okay, so the idea is that Alice and Bob know which permutation they chose, the adversary in the middle doesn't, and the permutation should be random-ish, meaning that if I pick a key at random, it should be at least hard to tell which one I picked, and we'll get there. All right? So I want to just cover this one point. We talk about this idea of the permutation being random-ish. How many possible permutations are there? If we have a function that goes from 64-bit inputs to 64-bit outputs, can anyone tell me how many possible permutations there are? I hope I didn't put it up there. Oh, crap. How many possible permutations are there?
To the 64.
A lot of permutations, a lot of possible permutations. Remember, a permutation is literally just a unique mapping from 64-bit inputs to 64-bit outputs. So there are 2 to the 64 factorial possible permutations. That's a lot. DES does not have 2 to the 64 factorial possible keys. It only has 2 to the 56. So it's really a much smaller number of keys. And so it turns out that we have to make an assumption. DES is clearly not a random permutation. But what we have to do is we have to call it something. And so the idea is that we want a block cipher to be what we call a pseudo-random permutation. That is a very concrete meaning. It means that if I pick a random DES key, one of the permutations that DES defines, then I give you access to that DES cipher, and I encrypt some stuff for you. You should not be able to tell the difference between that and another world where I actually picked one of those and all of those 2 to the 64 factorial random possible permutations really at random. You should not be able to tell which one that is. So that's the technical definition of pseudo-random. Okay? So an attacker who doesn't know the key can't tell whether you're encrypting using a random, really random permutation or one sampled from the pseudo-random permutation family. And so that's the definition. It's not terribly important now, but it will become more important later on in the class. I want to look inside DES. I want to show you what actually happens in DES because it's one of the coolest designs. But I don't want to use this example. I don't want to use this diagram because it's crappy and it doesn't make it clear what's happening. Okay, so back in the 70s, the people who built DES had a problem. They had come up with a bunch of really good ideas for building stuff that took in data. They'd come up with these kind of boxes called S boxes that took in a few bits of data and produced a few bits of output data. And they'd actually managed to make these functions somewhat nonlinear. So they kind of did a good job of scrambling data. All right, and they found that they could like assemble a bunch of these boxes together, and they could do lots of stuff, and it would do a really good job of taking data and kind of putting it through a blender and producing very complex looking but unrelated data, random looking output. But it turns out that by assembling these boxes, you don't get a permutation. You can't decrypt things that have been sent through a blender for the same reason you can't, reassemble something that you put through a blender. These things really just shred data. They don't allow you to invert that shredding. So they had to come up with a way to use these boxes they built to actually do something that was invertible. The solution they came up with is called a Feistel network, and it looks like this. So let's say this is our plain text. And remember in DES, our plain text is 64 bits long. Okay, so the first step of using a Feistel network is you cut the plain text in half. So each of these is now 32 bits long. And we're going to assume that the ingredient we have for building the Feistel network is this function I'm just going to call f. It takes in a piece of a key, and it takes in some data, and it produces, I'm just going to call, intuitively, I'm going to call it shredded data. It's some function of this data and this key that looks very unpredictable and kind of random. Just go with that for now. It's not very precise. Okay, so what we're going to do is we're going to take the left 32 bits, and we're going to feed them into our function f along with at least a piece of our key. Okay, so this is going to produce garbagey looking data. but not invertibly guaranteed looking.
But so, yes. So if it's just one function, it is reversible.
Nope.
It's just one.
Nope. In fact, this is not even guaranteed to be a permutation. It could be that like two different inputs could produce the same output, so you can't even invert that. So this function f, the function f by itself is not invertible. It's a blender. You put in some data and a key, and it produces data out that is very much not related to the input data. It's very difficult to kind of predict if you don't know the key what the output is going to be. But it's not itself invertible. So that's our basic ingredient. We have this function f that scrambles data but is not invertible. How do we turn this into something that is invertible? That was the problem that they were trying to tackle. Okay, so the way they did it was they built this network using the function f as an ingredient. So they'd take an input that's 64 bits long, they'd slice it in half to take the leftmost 32 bits, and they would feed that into f along with the key. And as we said, this produces output that is, like I said, blended. It's very much unrelated to the input. It's not predictable. It looks random. They would take that output, and they would XOR it with the rightmost 32 bits. And that produces an output. I'm just going to draw that down here. Okay, so these are each 32 bits. Okay, and so this is 32 bits. And so now we have shown how to derive this section of the output. How do we get the left side? Anyone quickly tell me? Okay, so we're going to take the right side, which we've kind of already drawn a line down here. What are we going to XOR it with? Anyone?
Just in place replacement.
What's that?
Just in place replacement.
Oh, we could do that. That would be, I mean, we might, so in this diagram, that is what we would do in a single round. But just to sort of simplify this, we could take the right side, and we could actually take this, and we could XOR it with, and I always get this wrong, but let's try it here. We could XOR it with this value. Let me try, got that right. No, I'm sorry. We would XOR it with this, okay? And we would, sorry, terrible graphics here. We would put this into the left side, okay? I hope I've got this right in my terrible drawing. Okay, so the basic idea is now let's say I want to invert this. I take this right side, okay? I have to be able to recover, I probably have gotten this wrong, haven't I? Let's see, nope, yeah, that is totally wrong. I'm gonna totally screw this up. Let me go back to my diagram, just trying to do this myself because it was terrible. Okay, so we have our plain text, all right? So we take the left side, we take the right side, we feed it to the function f, and we XOR with the left side plain text. And that comes down here and gives us our right side. Okay? To do this again, we can take the right side, and we can take that, and we can XOR it with the result that we just computed on the right side, and we can put that through f, and we can XOR it to get the right side. So let me see if I can actually do this correctly. Okay, yes. So we take this f, we take this, we feed it into f, and we XOR, sorry about this terrible drawing here, we XOR like this, voila. And that actually gives us two somewhat enciphered looking halves. Do not use this diagram as a reference to work with, because I'm still not 100% sure I've gotten it right. Let's walk through why, at least if I haven't totally screwed this up, this works. Yes?
Is this actually this, or what exactly is this?
This is a part of what's called a Feistel cipher. We'll get into how this is actually this in a second. Okay? So what they basically figured out was if this function f is a shredder, and we key it on both the key and the left side here, well, when we feed that into f, we'll get some data that is at least somewhat random looking. Remember, we said that in the one-time pad, if we XOR a random key with the plain text, what do we get?
Unbreakable.
Well, unbreakable, or at least a very well-ciphered random-looking output. And so that's exactly what we get here on the right side. It's a random-looking output. Good, so we've deciphered it. Similarly, if I haven't totally screwed this up, we take the, what's going into f? We take the output that we just computed, and we feed that through another instance of the function f, along with the key. And we XOR that with the, was I supposed to use the left side? Did I totally screw this up? Yeah, I'm sorry, guys. There we go, it's all fixed. Then we feed that into the left side, which is the part we haven't enciphered. Okay, now we get the left side of the message. Okay, so now we've actually enciphered both halves. Use this diagram, don't use mine. So the basic intuition is now we have used a piece of the message both to feed into this f function, We've gotten some output that's very random, and we've XORed with the other half of the message. And this is equivalent, if you believe the F function produces something that looks random, it's equivalent to basically doing a one-time pad encipherment of both halves of the message. How do we invert it? Well, let's say we have this part, half of the message, and we want to go back up. Can we do that? Yes, good. Okay, well, I'm not even 100% sure, so walk me through it.
So we take that bit of the message and we feed it through F
Okay, good.
with the key.
Yep.
And then we XOR that to get the left half. And now we've recovered the left, feed it through F, and then XOR it with the bottom right part, and then we have the message.
So it's invertible. It's invertible even though F itself is not invertible. We can go backwards and forwards through one round of this function. So what the people who designed DES realized was that if you did this multiple times, it turns out doing this once is not enough. You could stack these rounds on top of each other, and this diagram does a better job of showing that. You can stack them on top of each other, and if your function F is relatively strong, you end up that no matter how many times you stack these functions, the entire result is invertible just by going backwards up through the function. And so then they just basically had the problem to solve of how do they build the F function. And the way they did that is they tied together a bunch of very small nonlinear functions, each of which takes in about 5 bits, or 1, 2, 3, 4, 6 bits, and outputs 4. They tied these together. So this is not really that great of a function. It doesn't really output strong pseudo-random output. So instead of doing this like just a few times, they did it many, many times. And the idea there is that even if F is not really as strong as I've tried to make it out to be, by doing this over and over again, you actually increase the complexity so that by the time you get to the bottom of this 16-round construction, you have really made it very difficult to invert the resulting cipher. So there's two things going on here. One of which is if you have a strong enough function F, and I can get into what strong means, but if it's really a pseudo-random function, then just doing this process, I think about 4 times, is enough to build a secure cipher. If you have a weak function F, which is made just out of a bunch of little tables of bits, then you may have to do it more times. But either way, you can build a strong cipher out of relatively simple pieces using this technique. Yes?
What I don't understand is how if both of the 32-bit halves have gone through this dicing function by the time we get to this lower level, how without inverting the function F we're able to actually reverse it.
Well, the reason you can't see this is because I've done a really lousy drawing of this. But if you look at it, notice that the right side, if you take this bottom half on the right side, which you have because it's the output of this function, and you feed it back through the function F, right? Now you have this value here, okay? And so it's just, and now if you take that and you XOR what you have here on the left side, so now you have this input and this input, and so you can basically recover this value, so you've halfway inverted it. And now that you have this value, you can basically recover the other half just by following back to where its XORs go. So you feed this into F, which gives you this input, and you have this value, so you have this input, and you just XOR those two things, and wham, you get back to the top. I will do a much better job of drawing it with some actual notes next time for you guys, but that's basically the gist of it. So it's actually very simple to invert if you can compute F, and if you can do XOR. And so this is the entire Feistel network function. And it's really clever, and it comes up over and over again in cryptography. We're going to talk about a piece of RSA pattern called OAEP that is just a Feistel network without a key. So this is a pretty straightforward thing. Yes?
So how do you, as an attacker, invert the F function in order to do the encryption?
Right. So one of the things I mentioned was that your key is one of the inputs to the F function. So by the way, when I say data encryption standard, I mean this was a standard. So they published the algorithm, the entire DES algorithm, with the description of how this F function worked in the Federal Register. So F is a public value. In fact, F is actually composed out of these little things called S boxes that are all wired together like this. But this is the internals of what's inside of F. So this is well known. What isn't known is the key. And F, it turns out, takes some bits of the key and some bits of the plain text each time you actually evaluate F. And it's those secret bits of the key that make the cipher secure, not the design of F, which everybody knows. Badly drawn, but that's the gist of it. All right. So this is what happens inside of these. There's also a part of DES called the key schedule. You can't fit the entire key into every invocation of F. So what happens is the key is actually broken up into what are called subkeys, and it's done using this process of rotating and truncating the keys. So you take 48 bits of the key and you put some bits into the F function each time. And so there's this sort of separate process inside the DES. Okay, so we'll go over the design in more detail later, but this was the basic idea. If you get past what's inside of F, and you just treat it as kind of a blender, this is the basic intuition for why it works. Any questions? Yes.
Why didn't DES use a 64-bit key?
So DES started out with a 64-bit key. It was originally a cipher called Lucifer, created by IBM. But the NSA told them that they didn't want to have a 64-bit key, presumably because it was too hard to crack. There's a lot of history with the NSA making design decisions that actually either strengthened or weakened DES. The most famous story is that right before DES was finalized, the engineers at IBM shipped it off to the NSA for analysis. And when it came back, the design of all these little S boxes had been changed. And nobody explained why or what the change was, but IBM went ahead and just finalized it and said, okay, this is our design. And that's what became DES. It turned out that about 3 or 4 years later, somebody invented a technique called differential cryptanalysis, which it turns out, when you apply it to the original design, before the NSA changed it, worked very effectively against DES. But when you applied it to the revised design created by the NSA with these new S boxes, did not work. So the NSA clearly knew about differential cryptanalysis and was a few years ahead of the academic community. A few years later, about 2 or 3 years later, somebody came up with a technique called linear cryptanalysis. And it turned out that DES was vulnerable in its final form to linear cryptanalysis. So that gives an indication that at that time, the NSA was maybe 5 years ahead of the academic community, but no more than 7 or 8 years ahead of the academic community, because they found one attack, but not the other, or at least they haven't admitted they found it. So we learn things about what the NSA knows from these kinds of contributions. All right. So there are clever attacks like what I just described on the DES cipher. Some of them are linear cryptanalysis, some are differential cryptanalysis. They are not really that interesting in the sense that the real attack, which we've already discussed against DES, is the fact that it has a very small key size, 56-bit. What's the practical solution to this? How do people use DES when they must use it in practice? Has anyone ever seen DES deployed in a real system? There are still some systems using DES. And as we discussed a little while ago, they're not using it in its normal form, because that takes an hour break. So how do people use DES if they must use it? Good. What does that mean?
They basically use this 3 times in a row.
That's right. Okay, so DES, triple DES, is literally just the process of applying the encipherment or decipherment function in different orders with different keys. There are actually 2 forms of it. One of them is called EDE, and what it does is you encipher with 1 key, you decipher with a 2nd key, and then you encipher again with a 3rd key. Okay? And then the result, sorry about that, that comes out of that is your ciphertext. So it's 3 times as expensive to encipher anything. You could do it in hardware, and then you just have more hardware. But this was actually a practical solution. How big is that key? And you have 3 of them. Yeah.
No, I have a question.
Sure.
What does it mean by deciphering with a different key?
So you're picking 3 random 56-bit keys. You're setting up one instance of the encipher algorithm with the first key. You're taking the output of that and you're feeding it into the decipherment algorithm, but with a different key. If you fed it in with the same key, what would happen? It would just invert, right? So you're picking a different key, and then you pick a 3rd instance with a 3rd key, and now you encipher with that, and you get something out. Okay, good. Now, people can use, interestingly enough, there are actually 2 variants of triple DES, one of which is 3-key triple DES, which is what we just described there. And the other is called 2-key triple DES. Okay, 3-key is very obvious. You just do EDE and you're done, 3 keys. What's the key size of that? What's 3 times 36? Is that 130?
168.
Good, okay, good. So yeah, 168. You use 2-key triple DES, what's the key size of that?
112.
Good, 112 bits. Why do we do this EDE thing when we want to use 2-key triple DES? Assume that I am building a system in hardware that has to support either 3-key triple DES or 2-key triple DES. And I don't want to change my circuit depending on which one you're using. Yes?
Because that also works for 2-key.
Why?
Because you encrypt with key 1, decrypt with key 2, and then
Or decrypt with key 1.
and
then encrypt with key 2. So this 3-level cascade can support 2-key triple DES just by putting the same key into 2 different positions. Okay, so that's triple DES. Triple DES has a long key. If you use it in its 3-key variant, it has a 168-bit key, which is actually longer than AES 128-bit key. So it seems really good. What's the weakness of DES if it's not the key size? If we're using triple DES, are there any weaknesses that we know about in DES if we go to triple DES? How do we attack it? Where does it break? This is just a trivia question. Anyone know? Yeah.
If you use the same key for all three, that doesn't.
If you use the same key for all three, that would be single DES, because you'd just be encrypting, decrypting, and then encrypting together. So don't do that. Please don't do that. Okay. One of the weaknesses of DES, which we'll talk about a little later, is that it has a small block size. 64 bits is not very big. It turns out in some modes of operation, which we'll get to soon, there are actually things that can happen in the cipher that are collisions. And this is not related to the key. The key can be very large. But the fact that there are only 64-bit input and output blocks is actually a problem that is sometimes an issue with real schemes. It actually breaks things like TLS. We'll talk about that later. Okay. The algorithm that we are probably the most popular block cipher today is something called AES, which stands for. I have no idea what you guys just said, but I think you got it right. Advanced Encryption Standard. It was a NIST open competition, not designed by the NSA and the company. It was an open competition. Lots of people submitted their proposals. This was in the late 90s. There were 5 finalists. The one that won is called Reindl, which is a combination of the designer's 2 last names. There were several others. Really different requirements. Finally, this had to be fast in software, not just in hardware like DES was. Had to have a much larger block size for reasons we'll get to. And of course, larger keys all the way up to 256-bit with options for 128 and 192. These were the hard requirements. Reindl won. I'm not going to spend a lot of time on it, but basically Reindl is designed to work with matrices of bytes, where you basically have these 4x4 byte matrices. It has a 16-bit block, which makes it very efficient. And it basically just applies a lot of different operations, substitutions, matrix multiplications, and so on, until you end up at a ciphertext. And the design is not terribly interesting, but the basics of it are the same. It's still a block cipher. It just has a larger block size and some different options for key size. Okay, so the question I want to get to now is how do you go ahead, I don't know why this is review, how do you encrypt things using a block cipher? We know that these block ciphers work in chunks of data. So how do I go ahead and encrypt a file? Okay, so could I do this? So this is, since I've got this slide up, could I just break the file into a bunch of chunks? Well, I don't know why I have this slide up. The slide needs to go away. So let's say I take my file and I break it up into, let's say we're using AES, 128-bit chunks. And I pass each one through the encipher operation of the cipher, one at a time. Why does that not sound like the best idea? Or is that a good idea? Yes.
The last one might not have 128 bits.
Okay, so I add some padding to make sure that the resulting file is a multiple of 128 bits. Good. Now I chunk the file up into 128-bit chunks for AES, and I pick a key, good key, and I go through one block at a time and I encipher each one. Yes?
If you padded a lot and you know how it padded, you can recover the key.
Let's assume you can't do that with AES, because it actually is very hard to do that.
It's just going to be the same.
Hold on a second. Yes? The key is the same for each block. Yes. We're going to pick one key for this message. I'm going to take, let me be a little more structured in how I express this, okay? So I've taken my file. My file looks like this. I'm going to chunk it up like this. And I'm going to assume that each of these is 128 bits long. I'm going to take each one of these. I'll call this M1, M2, ... I'm going to encipher using AES under some key, M1 to get C1. And I'm going to do the same thing for M2 and so on. Okay, so I'm going to end up with a message that looks like this. Okay, so this is my encryption algorithm. What could go wrong? Yes.
There'll be patterns in the ciphertext.
Why will there be patterns in the ciphertext?
Because this is just like visionaire. Like if similar things get encrypted with a similar key, it will result in similar ciphertext.
Good. Okay, so block ciphers are deterministic. There's no randomness in them. Once you fix a key, which we have through this entire file, every time the same bit pattern, 128-bit pattern, goes into the cipher, we're gonna get exactly the same 128-bit output pattern. Does anybody disagree with that? Yes,
Well, question, so isn't there that function f which depends on a key?
but we've already fixed the key. We fixed one key for every single block. We're using that.
Does it have to be the case?
Well, we're talking about how to fix that.
Let's not look inside the cipher. The function f is inside of DES. But generally, the design of a block cipher is that if I choose a key, then from that point on, every time I encrypt the same message, there's no randomness inside of it. Every time I encrypt a message, it's a function. It will produce the same output. Okay? So if I fix a key for this message, then every time I encrypt a message block that has the pattern of M1, I'm going to get exactly this C1 value out. So yes.
If C1 is coming out and it looks kind of pseudo-random, could we then XOR that back with a key and use that as a
Oh,
new
you're
key?
getting crazy now. You could, maybe, I don't know.
Okay.
It's possible. Something could happen. But let's not go there.
Okay.
Now you're trying to fix the problem. I
Oh,
just want
okay.
to know what the
Oh,
problem
okay.
is.
Sorry.
You all sort of see why that could be a problem. Why could this be a problem? So remember, in Visionaire and in symbol substitution ciphers, we leaked information about the patterns of the underlying data. Same problem here, right? So we have a deterministic function. There's no randomness. We picked a key. So we're always going to know, let's say that M1 is a bunch of 0 bits, because maybe my file starts with a bunch of zeros, and it turns out M2 is also a bunch of 0 bits. Well, the stuff that comes out in C1 and C2, the first 128 bytes may be really random and unrelated to those 0 bits, but if both of the first two plaintext blocks are zeros, then the first two plaintext blocks of the output message are going to be the same. They could be random looking junk, but they're going to be the same random looking junk. And so that's going to reveal patterns. And so, for example, here's another one. If we just take this, just like Visionaire, we assign letters to indicate 128-bit bit patterns. Well, if I have 3 padding blocks on the end of the message, I'm going to see 3 repeated ciphertext blocks in the ciphertext. And that's going to tell me something about the resulting message. And so it'll look something like this, and that pattern will be obvious. Now, you guys have probably seen at least one of these pictures. Picture down here is a picture of this is a TIFF file of the Tux Linux Penguin that was passed through ECB mode encipherment. I think they used AES. And you'll notice something, right? This is not like you have to be a sophisticated cryptanalyst to see that the encryption is not working very well. Why? Why is this TIFF file particularly vulnerable to this attack or to this flaw? What is it about TIFF files? Yes?
It doesn't contain that much information. It's really stark differences in colors.
Yes.
So even if you encrypt them, the differences are what matter.
Right, so lots and lots of repeated patterns in particular, because the pixels in a TIFF file are very wide, and so all of these white pixels are basically long sequences which repeat over and over and over again throughout the file, and just that repetition is enough to create a really obvious visual view when you open the encrypted file. So it turns out that this is really, really weak. Okay, this is another example that I actually came up with when I was doing consulting years ago. You can't see it very well from back there, but mostly when you open up, by the way, a really good way to understand ciphertext, I'll be done in a second, is to open them up in a graphics program like Photoshop as a 1-bit black and white file. That's what we did with this one. Most of it looks really random, really well encrypted, except for these tire tracks here and here and here. This is an encrypted executable file, and those tire tracks, I zoomed in on one of them here, are actually segment breaks between pieces of code, which, if you probably look at the plain text, are probably repeated strings or maybe just zeros. But when they get encrypted, they turn into these very obvious patterns. Now we know where the segments of code are. When it gets loaded into memory, we'll know where those are too, and we know exactly where to hook in to break this file encryption system or this executable encryption system. Okay, I will see you guys on Wednesday.